Now let's look at biogas technology in developing countries. The first thing we may want to look at is how many of these digesters are existing in developing countries. About 45 million digesters are currently being in application in developing countries, of sizes ranging between 1 cubic meter to 40 cubic meters. Now, with this volume nomenclature of digesters, between 2 and 15 cubic meters, they are considered as domestic biogas system, and greater than 15 cubic meters, they are considered as community biogas system. Now, when we look in terms of numbers, the Asian continent has the greatest share of digesters in use. For example, China has a lion's share of 38 million digesters. But when we look at the African continent in general, the adoption of this technology is still very low. In terms of the type of designs that are disseminated in developing countries, we have mostly the floating drum, the variety of the fixed domes, and the plastic digester, and of recent fabricated digesters that are disseminated. All of these designs functions on the complete mix principle, and they are wet digesters, which means that the total solid that is introduced in the digesters have to be less than 10% for effective functioning of the system, and they are designed to operate within the mesophilic range of temperatures. They are very simple and without mixing facilities or complicated measuring facilities. So we have here, for example, the Chinese fixed dome and its derivative, the Nepali fixed dome, the plastic or tubular digester, the Indian fixed dome, which is called the Din Badu, which means the design for the poor people, and the Vietnamese fixed dome, and the floating drum, of course. When we look at all the designs, we see that the fixed dome is more or less the predominant design that mutates from one region to the other, and the reason is simply because of its robustness and maybe the cost, and the shapes differ simply because they search for better performance. Now, the components that are common to all these digesters that are disseminated in developing countries includes the inlet tank, the digester tank, then we have the gas storage, which could be incorporated to the digester like in the fixed dome and the floating drum, or it could be separate from the digester like in the case of plastic digesters. Then we have the outlet tank, and then of course the pipeline to convey the gas to the consumer point. And the consumer point could be a burner to directly burn the gas, or it could be an internal combustion engine, or it could be a point at a refuel station to refill cars. So we have here the components put together in the Nepali fixed dome design. On the left hand, we have the inlet, and in the middle, we have the dome, which rests over the digester, which is below, we cannot see it. On the top right-hand corner, we have the outlet chamber. Normally, when the digester has been completely constructed, you wouldn't see the dome and the digester because it is buried on the ground. About the performance of digesters that are disseminated in developing countries, the first parameter we want to use in assessing the performance or analyzing the performance of the digester is asking whether they are functioning or not, as the functioning state of the digester. Here, the results are not very, very encouraging. For example, by 2007, 60% of the digesters that existed in China at the time were in good functional state. In India, by 1990, 60% were functional, and in Bangladesh, by 2005, 47% were functional. For the digesters that are disseminated in Africa, we don't have information, or in the literature it's difficult to have information on the functional state of these digesters. But one thing we can note from this functional state of the digester is that the failure of digesters is believed to be due to poor design or poor construction, or simply because the digester are poorly operated, for example, not fed at the right time, or not fed with the right substrate, or not fed at all, so they don't function, as well as inadequate mixing in the digester is responsible for the poor functioning state of the digester. More technical terms, we can look at the performance of the digester in terms of how much biogas is produced, the production rate and the productivity, and in the stabilization of pathogens that may be found in the organic substrate that is used. The technical performance in terms of biogas production rate varies depending on the type of design and also on the geographical location. But what we can note is that in terms of pathogen stabilization, all the designs perform excellent in eliminating pathogens like coliform. Several strategies have been used to ameliorate or improve the performance of the digesters. These include use of a mixture of feedstock, for example, using a combination of pig and fowl dung to run the digester, or a combination of cow and pig dung to run the digester. This strategy is simply to increase the CN ratio, as we saw earlier, to increase the CN ratio in order to improve on the nutrient supply to the digesters, and hence encourage more gas production. Manipulating the operating temperatures is also one of the strategies that has been used to improve on the performance. We have seen that most of the digesters that are designed to function within the mesophilic range of temperatures. However, from the literature, the digester ends up operating between the lower mesophilic range and the upper psychrophilic range of temperatures. So they don't function at the optimal temperature. So techniques to improve on the operating temperatures include heating the substrate before feeding into the digester, or composting on the digester in order to increase the temperatures, or the use of greenhouse effect, which is called solar canopy. This is very popular with the plastic digesters, or simply insulation of the digesters, like is the case with most of the fixed dome digesters that are buried on the ground. Another technique is to increase the amount of solid material that we introduce into our digesters. We saw that most of the digesters disseminated in developing countries are completely mixed, which places a constraint on how much solid goes in, and we saw that the amount of solid that can go in is only 10% of the amount of feedstock that is fed into the digester. What does this mean? It means that if we say we are feeding the digester with 50 kilograms of feedstock, it means that only 5 kilograms of solid is introduced into the digester. The remaining 45 kilogram is water, which is in it, which doesn't help in the digestion process. So we can increase the amount of solid that is introduced into the digester. In that case, we increase the fuel and therefore increase the output. But if this is done, the issue of mixing may arise. As we've already mentioned, mixing can improve on the process. Most of the digesters we saw are very simple without mixing mechanism, but gas circulation has been demonstrated in some of the digesters, and the use of manual screws to improve on the mixing in the digesters. But this is without compromising the engineering structure of the design. One other very simple way of improving mixing in the digester is modifying the components of the digester. For example, if we look at the various fixed dome digesters, from the top right hand corner we have the original Chinese fixed dome. If we look at the inlet, it's very large, but the digester in the middle right hand corner has an inlet that is smaller. This is an attempt probably to increase the speed at which the feedstock enters the digester, and therefore can agitate the content of the digesters. So we can also see the different structures from the Indian Din Badu at the bottom right hand corner to the Vietnamese design in the middle bottom and the Nepali design at the left hand corner. We see that the inlet and the outlet have different configuration, and the bottom of the digester have different configuration. All the variation in the design of the components is to achieve better mixing. To conclude, biogas technology is a very mature technology that can be used to solve most of the energy problems that we have all over the world, in developing countries in particular, because of its social and environmental advantages. However, there are a variety of process, strategy, and digester designs that are available, which depends on which are adapted for different geographical, social, environmental contexts. Therefore, choosing a design will require a design for a particular region will require a careful decision making. And the performance of the digesters, though not very high, is satisfactory, and the poor functioning of the digesters are linked to gas leakages, insufficient mix feedstock that is used, blockages in the pipe, in the conveyor pipes, or lack of maintenance. Sociocultural issues also contribute to the mediocre performance of the digesters. One thing also to note to conclude is the technology is relatively low adoption of the technology in Africa, mainly due to high cost and probably the non-availability of appropriate designs. And lastly, the information we have about the performance of the digester is not from the field, so we have very few field evaluation of the performance of the designs that are disseminated in developing countries. So I've come to the end of the presentation. So I will refer you to chapter 4 of the book on the title Renewable Energy for Unleashing Sustainable Development, and the Swedish Center for Swedish Biogas Center for more information on biogas technology. Thank you very much for your attention.